What I'm going to be presenting today is a filtering algorithm for constraint-based scheduling, which is called edge finding. Now, constraint programming is a method used for solving combinatorial problems, solving or optimizing combinatorial problems, I should say. We have a set of variables, each with a domain of discrete possible values, and then a set of constraints over those variables, which specify the combinations of values among the various variables which can be present in a feasible solution. A filtering algorithm is an implementation of one of these constraints. It takes a certain set of variables and it removes values from the domains of those variables when they cannot participate in a feasible solution. Now, edge finding is a filter which has been long used in disjunctive scheduling. That is, scheduling applications where only one job gets scheduled at a time. And it's also applicable to cumulative scheduling. That is, scheduling where we can have several jobs using the same resource at the same time. But it has a much higher complexity for cumulative scheduling, which has always hampered its usage. The standard algorithm for cumulative edge finding has a complexity of kn squared, where n is the number of tasks that we're scheduling, and k is the number of discrete capacity requirements among those tasks. But in 2009, Peter Willem proposed a new cumulative edge finding algorithm, which was significantly more complicated in its implementation and used a novel data structure that had to be constructed, but achieves a complexity of kn log n. So my project, which was performed at the Swedish Institute of Computer Science, was to implement and evaluate the new Willem algorithm for possible inclusion in the Sixtus Prolog constraint solver, replacing the standard edge finding algorithm, which was already there. So what I'm going to cover today is a quick overview of cumulative scheduling. Then I'll take a look at just exactly what it is that edge finding does and how we can do edge finding using Willem's algorithm, and then a little bit of what I did moving towards an implementation of this algorithm. So, the cumulative resource scheduling problem. We have a set of tasks which share a finite resource which has a constant capacity. So here we have a resource of capacity 3. At each interval of time, we can schedule tasks that will use a total of 3 units of the resource. Each of the tasks is defined by the amount of resource that it requires, which is labeled as C here, which we'll consider to be constant throughout the duration of the task, and also a fixed duration, so the task always lasts for the same amount of time. Tasks are also defined by the domain of their possible start times. So this domain is bounded, in this case, by 0 on the lower end, which I've labeled as EST for earliest start time, and the upper bound of 7, which is the latest start time for the task. But since the duration of the tasks is fixed, it's equivalent to talk about the last completion time of the tasks. We can either talk about last start time or last completion time. But generally, we talk about the last completion time instead, because algorithms such as edge finding are symmetric over adjusting the earliest start time and the last completion time. So for the rest of the talk, I'll focus on how we would adjust the earliest start time of the domain of a task, but you can use the same algorithm to adjust the latest completion time as well. We can also lift these concepts to sets of tasks. So here we have several tasks, and if we look at the set of tasks A, B, and C, the earliest start time of a set of tasks is the minimum earliest start time of any task in that set. So in this case, for A, B, and C, it's 0, and the last completion time for the set is the maximum last completion time for any task in the set, so in this case 5. And furthermore, the energy of the task, which I forgot to mention. So for an individual task, we have the duration and also the capacity requirement. The energy of the task is simply the product of these two quantities, so the area of the task on the graph. And for sets of tasks, the energy of the set is simply the sum of the energy of all of the individual tasks. So the cumulative constraint enforces the rule, essentially, that for every unit of time, the sum of the capacity requirements of every task that has been scheduled to execute at that time has to be less than or equal to the capacity of the resource. Now, this is NP complete. It's essentially like a bin packing problem. So we don't actually completely enforce the cumulative constraint. Instead, we have a series of filtering algorithms which are relaxations of cumulative. They are weaker than cumulative. They will remove some values which cumulative would theoretically also remove, but they won't get all of them. And edge finding is one of these elastic relaxations of the cumulative constraint. Furthermore, we'll only enforce bounds consistency, meaning we will attempt to tighten the lower bound of the possible start times and the upper bound of the possible start times, but we won't attempt to remove any infeasible values from inside that domain. We're simply shrinking the size of the domain. So, what is edge finding? If we consider the set of tasks A, B, and C, which I'll refer to from here on out as the set of tasks theta, edge finding asks the question, is there a feasible schedule in which all of the tasks in theta and the task D, which is not in theta, can be completed by the last completion time of theta? And if we take a look at these tasks, we can clearly see we can shift A, B, and C around, but there's no way that we can shift them around enough for D to be completed by the last completion time of theta. So this means we can conclude that in any feasible schedule, the end of the task D must come after the end of every task in the set A, B, and C. And we can then adjust the earliest start time of D accordingly. So in this case, we see that we could adjust the earliest start time of D to 3. How do we figure out exactly what the updated earliest start time of this task is, though? The way that we do this is we treat the energy of the set theta as though it was completely elastic. So we keep the energy of the tasks constant, or the energy of the total set constant, but we no longer worry about the individual durations and capacity requirements of the tasks. Instead, we put it wherever we want in this interval. So we break it up into 2 parts. First, we schedule as much of the energy of that set as possible without interfering with the scheduling of D. And then we schedule the rest of the energy as early as possible. So we get a lower bound on the adjustment that we can make to the task D. And since all of these values are considered to be discrete, we round it up. So we get a very quick calculation that lets us see that we can update the earliest start time of D to a time of 3. But we can actually do a little bit better than that. If we look at the set of tasks B, C, so for the moment we ignore the task A, this didn't seem like a very interesting task or set of tasks at first, because we can actually schedule D before the end of B and C without violating any of the resource constraint. But since we already know that the set A, B, C must come before D, we know that each of its individual tasks must come before D. So now we can take the energy for the tasks B and C and reschedule that elastically in the same way, and that gives us a new earliest start time for D of 4. So not only do we have to compare each task to every other set of tasks in order to find a set of tasks that precedes it, we then have to compare it with each of the subsets of that set in order to find the one that gives us the strongest bound update, which isn't great complexity. Fortunately, we don't have to look at all of these sets of tasks. Intuitively, if we have a fixed time window, we would like to get the set of tasks that all must be scheduled inside that task window that is the largest. So in other words, here we've got A, B, and C versus A and B. They both have the same start and completion times, but clearly A, B, and C has a higher energy than B. So we define what's called task intervals. These are sets of tasks which are bounded by the earliest start time of one task on the bottom and the last completion time of a second task on the top, and include all of the tasks in between. And an elastic relaxation algorithm, like edge finding, only needs to consider task intervals. It can ignore all of the other subsets. And since we've only got two bounds then to consider, we've reduced it to n squared sets of tasks that we need to look at. And that's the source of the n squared term in the complexity. So, one way that we can improve that complexity then is to find some way with a complexity lower than n of identifying one of these two bounds. And that's exactly what Willem has done in this paper, which is called, I don't remember the exact title off the top of my head, but it's using theta trees to do cumulative edge finding. And a theta tree is a binary tree. We arrange all of the tasks that are underneath a certain upper bound for our task interval as the leaves of this binary tree. And they're arranged in order of increasing earliest start time. The interior nodes of the tree then calculate values for the sets of tasks in their own subtree. And the values that we compute are the energy, which is just the sum of the energy of the individual tasks, and the energy envelope, which depends on both the energy of the set and also the earliest start time of the set. We use energy envelope because we can quickly compute it using the binary tree. So the energy envelope for an interior task, or for an interior node rather, is the maximum of either the energy envelope of its right child or the energy envelope of its left child plus the energy of its right child. Now, if we had to set this entire tree up for every potential upper bound, that wouldn't be so great. But we can set it up once for all of the tasks, so for the largest upper bound. And then we remove the tasks from the leaves in order of decreasing last completion time. So we always have a task interval, we're just shrinking them. And when we remove one node, we can update the energy envelope value in the root node in log n steps. And the energy envelope